So, welcome to today's deep dive. We are thrilled you're joining us because, well, we are tackling something that affects almost every physical product you buy. Usually, when a company runs out of space, the solution feels pretty obvious.
Right, it's just a geometry problem.
Exactly. I mean, you have a box, the box is completely full. So, obviously, you just need a bigger box.
Yeah, you just pour more concrete, or you go out and sign a massive new commercial lease.
Right.
Because the prevailing mindset in industrial operations is that spatial exhaustion is just a hard physical limit. Like, the logic dictates that if the racks are full and the aisles are congested, the only variable left to alter is the actual square footage of the facility.
But then, you look at the internal operations of these modern industrial warehouses, and suddenly that geometry problem is revealed as a complete illusion. I mean, we are looking at these massive million-square-foot facilities that claim they are bursting at the seams,
Yeah.
but the reality is they really aren't out of space at all.
No, not even close. They are quite literally drowning in their own empty air. It is the absolute definition of broken spatial logic.
Which is wild to think about.
It is. And the sources we're diving into today, these detailed industry methodologies from Avalon CSC, Geodis, and systems architect Prasad Bond, they all point to this exact phenomenon. Expanding the footprint is rarely a structural necessity.
Right, it's a mask.
Exactly. It is almost always a mask for operational inefficiency.
So our mission today for you listening is to explore this hidden industrial superpower. We're going to look at how operators transform these chaotic, overflowing warehouses into sleek, hyper-efficient machines, and they do it without pouring a single drop of new concrete.
Which is the fascinating intersection here. We're talking about physical engineering, artificial intelligence, and really just basic operational survival all coming together.
Yeah, and by the end of our analysis, we're going to map out exactly how taking 52 weeks of historical warehouse management system data, WMS data, and pairing it with genetic algorithms recovers insanely expensive real estate.
And saves human bodies from walking miles of wasted steps every single day.
Yes, that part is huge. And we'll also examine how this exact software-first approach has become an incredibly lucrative model for bootstrap startups with limited capital.
But before we get to the algorithmic solutions, we really have to isolate the underlying pathology here.
We have to diagnose the illness first.
Right. We need to look at the physical reality of a poorly optimized warehouse and understand what Bond and the Geodis analysts actually identify as the core problem. And the breakdown fundamentally starts with how inventory is placed, or I should say how it is abandoned.
Yeah, the technical term they use in the literature is inventory digging, which I gotta say paints a really bleak picture.
It's a very physical, exhausting image.
It really is. Like, when I envision a modern supply chain, I picture seamless automation, robots zipping around. But the reality for a ton of these operations is that the fast-moving items, the things customers order every single day, are left in the darkest, furthest corners of the facility.
Which forces the workforce to walk miles across concrete floors, bypassing thousands of stagnant products, just to retrieve basic daily goods.
And the phrase Avalon CSC uses to describe this is kinetic friction.
I love that term. It sounds like a principle of advanced physics.
Right. But in an industrial setting, it translates directly to human exhaustion and vanishing profit margins. I mean, every unnecessary inch of movement represents human fatigue. From a purely financial perspective, the phrase they use is, distance is the enemy of margin.
Distance is the enemy of margin.
Wow.
Exactly. Because when workers are walking an extra half mile to pull a pallet that honestly should have been situated 20 feet from the shipping dock, the operation is bleeding capital through inflated cycle times.
And inventory digging takes that friction a step further, doesn't it? Because the workers aren't merely walking.
No, they are physically excavating.
Right.
They're digging through mixed pallets and poorly organized spaces, trying to find high-velocity SKUs that are just completely buried behind dead stock.
It totally bottlenecks the throughput velocity of the entire operation. But, this raises an immediate glaring question for me regarding oversight.
Sure.
Like, if this kinetic friction is so obvious on the warehouse floor and it's so detrimental to the margin, where's the control point? I mean, surely an executive board would audit the spatial efficiency of a facility before they approve a $5 million lease for a new building.
You would think so.
How does this level of disorganization survive corporate scrutiny? Are the managers just being lazy?
Well, the control point is the facility manager. And this is where we encounter what Mon describes as a profound organizational dilemma.
Okay, and unpack that.
So executive boards rarely have the localized data or the operational expertise to audit three-dimensional volumetric efficiency. They are looking at spreadsheets, not rack layouts. So they rely entirely on the facility manager's assessment.
Which makes sense on paper.
Right. But when kinetic friction slows down operations to a crawl, the manager often blames physical constraints. They draft reports showing 95% rack utilization and request massive capital expenditure for expansion.
Because that fundamentally protects the manager. I mean, reorganizing shelves seems infinitely easier than managing a massive construction project, right?
It does, but think about the optics.
Ah, okay. If a manager goes to the executive board and says, hey, we can fit everything in our current building if we just do a better job of organizing it, they are implicitly admitting that they have been running a disorganized, inefficient building for years.
Exactly. Expanding the footprint hides that reality. It acts as an insanely expensive rug to sweep the mess under.
Wow.
Bond actually refers to this as intellectual laziness masquerading as growth management.
That is a brutal assessment.
It is, but it's accurate. Doing the rigorous mathematical work to optimize the existing cubic volume requires acknowledging the failure of the current layout. Pouring new concrete just allows the operation to scale its inefficiencies rather than actually solving them.
That is wild. And this connects directly to the philosophical framework mentioned in the Avalon documents. They call it restorative engineering,
Yes.
which I found really compelling. We often talk about technology in terms of disruption, or replacing human labor. But the argument here is that mathematical modeling must exist to restore human safety, capability, and dignity.
Because the physical toll is the hidden tax of bad management. When we talk about distance being the enemy of margin, we aren't just talking about dollars. We're talking about actual human beings walking on hard concrete for 10 hours a shift.
Which destroys your knees, your back.
Exactly. Fixing the spatial logic of the warehouse isn't merely a real estate play. It removes the physical burden of historical disorganization from the bodies of the workforce. It eliminates these mindless punching tasks that a simple sorting algorithm could have easily prevented.
It kind of calls to mind a profoundly disorganized kitchen. Like, imagine inheriting a house where the previous owner decided to keep all the coffee mugs down in the basement.
Right, terrible placement.
Exactly. Every single morning, you have to walk down 2 flights of stairs, retrieve a single mug, walk back up, make your coffee, and then repeat it the next day. It is exhausting, and it destroys the utility of the kitchen.
It's kinetic friction in your house.
Exactly. And instead of moving the coffee mugs to the cabinet right next to the coffee maker, which is a zero-cost solution, the homeowner decides to spend $50,000 to build a second kitchen in the living room.
Which sounds insane when you frame it like that.
It totally does.
But the industrial equivalent of simply moving the coffee mugs is what the logistics industry calls slotting. And while the kitchen analogy highlights the absurdity of the problem, we really have to scale that problem up by a factor of 10,000 to understand the industrial challenge.
Because it's not just coffee mugs.
No, it's thousands of items. I mean, we all know the basic premise of slotting. Put the popular items near the front door and the heavy items on the bottom shelf.
It sounds like you're just telling grown men to put the heavy boxes on the bottom shelf.
Basically, yeah. But executing that logic across 100,000 unique stock-keeping units, or SKUs, with wildly fluctuating seasonal demand requires intense mathematical rigor.
Okay, so let's dive into that mathematical rigor. For someone totally new to this, how does a facility even begin to categorize the chaos? Because you can't just eyeball 100,000 pallets.
No, absolutely not. The first line of defense is categorizing stock into what we call velocity buckets. And this requires a ruthless application of Pareto analysis and ABC classification.
The 80-20 rule.
Exactly. The Pareto principle is the foundational baseline here. In almost any warehouse, roughly 80% of the outbound volume is generated by just 20% of the SKUs. Those are your A items, your high-velocity stock.
And the B and C items make up the remaining volume.
Right. But the immediate priority of slotting is actually to isolate the far end of that spectrum. We need to isolate what Geodis categorizes as dead stock and slow movers.
And the definitions for those categories in the sources were really eye-opening. Dead stock isn't just stuff that sells poorly. It is defined as items that have had absolute 0 orders in the past 6 months or more.
Half a year just sitting there.
Acting as physical blockades in prime real estate.
Yeah.
And then slow movers are defined as products sitting in the facility for more than 3 months with a weekly average pick rate of 10 units or fewer.
And the sheer volume of this stagnant inventory in a typical unoptimized warehouse is staggering.
So what's the first step they take to fix that?
Well, the actionable insight from the sources is immediate. One pilot program detailed in the methodologies involved doing absolutely nothing else but identifying this dead and slow-moving stock and physically relocating it to the deepest, least accessible corners of the facility.
Which makes sense. Get it out of the way.
Exactly. Just moving the physical blockades out of the prime picking paths resulted in a 30% increase in units picked per hour.
Wow, a 30% operational gain just from clearing the hallway. That completely validates the concept of kinetic friction.
It does. It's the lowest hanging fruit.
But once you banish all that dead stock to the back of the warehouse, how do you profile the remaining active inventory? Because the heavy boxes on the bottom shelf rule makes intuitive sense, but the Avalon and Geodes profiling methodologies go much deeper. They talk about cube utilization and this concept of crushability.
Yeah, crushability is a fascinating constraint because it complicates the basic logic of velocity.
Yeah, so.
Well, you might have a highly popular item that needs to be picked frequently,
Yep.
right? So your instinct is to put it right at the front. But if it's extremely fragile, say specialized light bulbs,
Yeah.
you cannot place it at the very beginning of the picking path.
Because of how they build the pallet.
Exactly. As the worker moves down the aisle filling their pallet, they are stacking items. If you put the heavy items like anvils or bags of soil at the end of the path, they will crush the fragile light bulbs that were picked earlier.
So the algorithm has to balance the velocity of the item against its physical density and fragility.
Right. You have to sequence the warehouse so the worker naturally builds a structurally sound pallet, picking heavy, durable items first and light. Fragile items last completely, regardless of whether the light item is technically a faster seller.
That is brilliant. The physical constraints overrule the pure velocity data.
Correct. And another crucial profiling method is analyzing the unit of measure, or UOM.
Because a distributor doesn't just sell an item.
No, they sell variations of packaging. They might sell a single tube of chapstick, a case of 12 tubes, or an entire pallet of 100 cases of chapstick.
Which means you have to zone the warehouse based on the picking method. Because a massive forklift grabbing a huge pallet operates in a completely different physical footprint than a human worker picking individual boxes from a shelf.
Exactly. The UOM profiling analyzes the historical data to determine the exact mix of these sales. If an item sells primarily by the individual unit, placing bulk pallets of it in the active pick zone is a massive waste of cubic volume.
Right, you're wasting the golden zone.
Right, so you zone the facility into pallet reserves, case picking aisles, and each picking zones for single items. And you have to strategically sequence how those zones interact.
And the most strategic method mentioned in the sources, I think, is profiling by what they call the order completion zone. This feels like the most advanced application of the data.
It is. It's very sophisticated.
Because instead of just looking at individual item velocity, the operators are running correlation matrices to find out which items are frequently purchased together.
It relies on affinity analysis. So if the data reveals that a specific cluster of, say, 20 SKUs out of 50,000 is responsible for entirely fulfilling 60% of all customer orders, those items are pulled from their disparate categories.
You can group together.
Yes, into a highly concentrated order completion zone.
It operates exactly like an express lane or a convenience kiosk at the front of a massive grocery store. Like, if 60% of people only want milk, bread, and eggs, you don't make them walk down aisles 7, 9, and 12.
No, you put a cooler right next to the checkout.
Exactly. Executing any of this, identifying the dead stock, calculating the UMM mix, finding those order completion correlations, it requires an immense amount of historical data.
Oh, absolutely. And this brings us to the operational fuel required for spatial logic. The algorithmic models cannot function on assumptions or gut feelings. They require empirical evidence.
Right.
Both Geodes and Avalon mandate a very specific data set. Exactly 52 weeks of rolling historical order data, refreshed on a weekly basis.
Now, why 52 weeks? Because, a quarter of data or a 6-month snapshot would seem sufficient to establish a baseline of what sells and what doesn't.
You'd think so, but a 6-month snapshot is highly vulnerable to seasonal distortion and supply chain noise. 52 weeks captures a complete, unassailable cycle.
Or it captures the whole year.
Exactly. It accounts for holiday spikes, summer lulls, and the natural product life cycle from launch to obsolescence. More importantly, it provides a complete picture of hits, which is the exact number of times a specific bin location is visited by a worker, and the total lines picked.
So if you don't have that full year...
Well, if you only analyze 30 days of data in July, the The algorithm will categorize winter coats as dead stock and recommend moving them to the back of the facility.
Which creates a catastrophic bottleneck when November arrives.
Precise.
But this highlights a significant structural problem within the industry, doesn't it? Like, if this 52 weeks of data is the key to unlocking a 20% reduction in labor costs and a massive increase in fulfillment speed, why isn't every warehouse doing this constantly? Where is the friction?
The friction lies in the software architecture of legacy WMS platforms.
The WMS vendors.
Yes, the warehouse management system vendors.
Hmm.
These vendors built their systems decades ago, often on highly proprietary on-premise databases. They operate as a siloed control point.
So they guard the data.
They guard this movement data fiercely because data extraction threatens their ecosystem. They frequently hide the historical logs behind expensive API paywalls, or they structure the export protocols to be so convoluted that a facility manager cannot pull a clean CSV file without paying the vendor for custom reporting services.
It is essentially a toll booth installed inside a company's own server room. The vendor holds the operational history hostage.
That's a perfect way to put it.
But assuming the facility manager navigates that friction, they pay the toll or crack the export protocol, they now possess a massive spreadsheet containing a year of transactional history. How does a software engineering team translate a spreadsheet into a three-dimensional physical change on the warehouse floor?
Well, the next phase is constructing a digital twin, because the raw sales history is useless without spatial context. The 52 weeks of data is paired with two crucial data sets. First, the SKU master data.
Which is what, exactly?
It includes the exact physical dimensions of every single product, the length, width, height, weight, and packaging type.
Okay, and the second data set?
The physical constraints of the building itself, the exact XYZ coordinates of every rack.
So you need the architecture.
Exactly. The structural dimensions of the facility, the precise volume of every storage bin, the racking height limits, and the equipment constraints. Like, can a human worker reach the third shelf? Or does that specific location require a reach truck?
So you feed the historical demand, the product geometry, and the architectural blueprints into the system.
And it generates a virtual, functional, 3D replica of the warehouse. A digital twin.
That's incredible. But the Avalon methodology explicitly notes an exception for greenfield scenarios.
Ah, yes.
Meaning a brand new warehouse being built from the ground up. In a greenfield project, there are no historical logs because the doors haven't even opened. How do you optimize spatial logic when the 52 weeks of data literally doesn't exist?
That's a great point. In that case, you transition from historical analysis to predictive benchmarking. You ingest data from similar existing distribution centers within your network to serve as a proxy.
Okay, so you borrow a twin.
Exactly. However, the focus shifts heavily toward equipment sizing and layout configuration before the concrete is even poured. You use the proxy data to determine exactly how many storage modules of each size will be required.
So you build the building around the math.
Yes. You assign zones, matching the ABC classification of expected inventory to specific rack types. So the facility is physically built around the mathematical model, rather than forcing the model into an arbitrary physical box after the fact.
Which brings us to the core of the operation. The algorithmic brain. We have the data and we have the 3D digital twin. Now we have to actually solve the maze. How do these algorithms predict future movement and mathematically minimize the travel distance?
The foundation of the system is predictive machine learning. GEODIS specifically highlights the deployment of the open-source Facebook Profit framework for this phase.
Which is really interesting, right? That a proprietary logistics operation relies on an open-source tool like Profit. Why use that specific framework instead of standard moving averages?
Because Profit is an additive regression model natively designed to handle highly seasonal time series data. It is fantastic at dealing with strong holiday effects and historical trend shifts. It doesn't just look at what happened. It models the underlying components of the demand.
But it's not applied uniformly to everything, is it?
No, absolutely not. The analysts process the data through an industry-standard framework known as ADICV squared to segment the forecasting approach.
Okay, let's unpack the math behind ADICV squared, because this is where the difference between basic reporting and advanced analytics becomes really apparent.
Sure, it stands for Average Demand Interval and Coefficient of Variation. It is a mathematical matrix used to categorize the volatility of every single SKU.
Let's start with the first part, the average demand interval, the ADI.
The ADI measures the frequency of orders. If an item is ordered every single day, the ADI is 1. If it is ordered once a week, the ADI is 7.
So the ADI measures the rhythm of the demand.
Precisely. Now, the second metric, the coefficient of variation, or CV squared, measures the magnitude of the swing in order volume.
How much is ordered at once?
Right. If you sell 10 units every single time the item is ordered, the CV is very low. But if you sell 1 unit one day and then 500 units the next time it's ordered, the CV is extremely high.
Which means you are dealing with massive spikes that can completely overwhelm a picking lane if you aren't prepared.
Exactly.
So how does the system combine these two metrics?
It plots every SKU on a quadrant. Items with a low ADI and low CV are classified as smooth.
Meaning they sell frequently and consistently.
Yes. The Facebook profit model can forecast these with extreme accuracy. Now, items with a high CV but low ADI are erratic. They sell frequently,
Okay.
but in wildly unpredictable quantities.
Okay.
And items with a high ADI and high CV are lumpy. They rarely sell. But when they do, the order is absolutely massive.
By segmenting the inventory through this matrix, the forecasting model applies different predictive weights. It doesn't treat a consistent daily seller the same way it treats a lumpy, unpredictable item.
Exactly. It generates a highly educated prediction of the future velocity for all 100,000 SKUs. And this predictive velocity is the input required for the genetic algorithms.
And this is the absolute core of algorithmic slotting.
It is. The genetic algorithm's objective function is to match the predicted item velocity with the optimal location rankings within the digital twin.
And location rankings aren't just about proximity to the shipping dock, right?
Proximity is a factor, sure. But location rankings also calculate ergonomic accessibility, the golden zone between a worker's waist and shoulders, and the sequence of typical pick paths.
So this is where the biological metaphor of the genetic algorithm is applied to physical space. The algorithm creates an initial population of random warehouse layouts.
Yes, each layout is essentially a genome.
And then it tests how well those layouts perform.
Right. It runs a simulation of a month's worth of projected orders against each layout using a shortest distance algorithm. This is what we call the fitness function.
So it calculates the exact total travel time required for a workforce to fulfill all those orders.
Exactly. And the layouts that result in the lowest travel times are selected to breed. Their characteristics are combined, and the system introduces random mutations.
Mutations, like swapping the locations of two SKUs.
Exactly. It does this to prevent the algorithm from getting stuck in a local optimum.
But wait, why use an evolutionary model with mutations at all? Why not just use a brute force calculation to find the absolute mathematically perfect layout from the start?
Because routing a workforce through a warehouse to pick thousands of items is a variation of the traveling salesperson problem. It is mathematically classified as NP-hard.
Meaning it's too complex.
The computational complexity is so immense that calculating every possible permutation of 100,000 SKUs across 50,000 bin locations would take a supercomputer centuries to process.
Wow.
Yeah, so the genetic algorithm is a heuristic approach. It rapidly evolves toward a highly optimized, though perhaps not theoretically perfect, solution in a matter of hours. The final output is a localized heat map, detailing the exact placement for maximum efficiency.
That is fascinating. But the heat map only tells you where the items live. The sources emphasize that slotting alone is insufficient. There is a synergistic sibling to slotting called wave pick optimization.
Yes.
Geodis argues that optimizing where the items are placed without optimizing how the workers retrieve them leaves massive efficiency gains on the table.
Because slotting dictates the static placement, but wave picking dictates the dynamic movement. A highly optimized layout is completely useless if you send a worker back and forth across the exact same aisle 5 times to fulfill 5 different orders.
Right. It's similar to a ride-sharing algorithm like Uberpool. You don't dispatch 5 different cars to pick up 5 people standing on the same block going to the same destination.
No, you group the passengers to optimize the route of a single vehicle.
So wave optimization dynamically groups incoming orders to minimize the travel path of the picker.
Exactly. The system analyzes a wave of incoming orders and assigns them a pick type. A batch pick consolidates the demand for a single SKU across dozens of different orders. The worker retrieves 50 units all at once, and they are sorted later.
Okay, and an order pick.
An order pick requires the worker to pull all the disparate items for one specific customer. The algorithm intelligently batches these based on parameters like carrier cutoff times or shipping destinations.
And once the wave is formed, how does the algorithm physically route the worker through the aisles?
It deploys A-star path finding and clustering analysis for aisle minimization. It identifies clusters of orders that can be fulfilled with the absolute minimum number of aisle entries. It correlates orders with complementary pick locations. Furthermore, it enforces S-shaped routing.
S-shaped routing, meaning the worker weaves through the facility in a continuous serpentine pattern.
Yes, the algorithm absolutely refuses to generate a pick list that requires a worker to walk halfway down an aisle, turn around, and walk back out.
Because that's wasted movement.
Exactly. S-shaped picking is highly intuitive for the workforce. They enter an aisle, traverse its entire length picking items on both sides, and exit at the opposite end, feeding directly into the next aisle.
And the combination of genetic slotting and wave routing creates the synergistic effect that routinely reduces total aisle visits by 15% to 60%, and in specific isolated scenarios, by over 80%.
Which is an astonishing recovery of lost time.
It really is. But what about highly automated facilities? Geodis discusses the application of this logic in environments utilizing autonomous mobile robots like locus robotics.
Right.
If a robot is doing the picking, does spatial logic still matter? I mean, a robot doesn't have knees to save, and it doesn't get fatigued.
It matters intensely, but the objective shifts. You move from reducing physical fatigue to managing automated congestion.
Oh, traffic jams.
Exactly. If a genetic algorithm optimizes a robotic facility by placing the top 50 highest velocity items in one single highly accessible aisle, what is the immediate result?
Every single robot on the floor is dispatched to the exact same aisle at the exact same time. You've created a massive robotic traffic jam.
Right. The velocity of the items bottlenecks the physical movement of the machines.
So the spatial logic has to adapt.
It does. The wave optimization system and the slotting algorithm must purposefully diversify the heat map. Instead of concentrating the fast movers, the algorithm distributes them strategically across multiple aisles.
To spread out the robots.
Yes, it generates multiple, varied wave templates to balance the robotic traffic load across the entire footprint of the facility. Geos noted that implementing this distributed placement strategy during a high-volume product launch resulted in a 50% reduction in automated congestion.
That is brilliant. The principles of volumetric efficiency are universal, whether you are managing human exhaustion or robotic battery drain. So we have established the theoretical model. We have the data, the genetic heat map, and the wave routing. But theory is cheap. I imagine shutting down a massive operational warehouse to physically reorganize 100,000 pallets is a logistical nightmare.
Oh, it could be.
How do they actually execute this physical move without stopping the daily operations?
Execution is where the Avalon CSC methodology really shines. They outline a highly structured, phased implementation plan that takes merely 2 to 3 weeks and introduces minimal disruption to ongoing operations.
They don't shut the facility down.
No, they do not shut it down.
Let's examine how they manage that transition.
It begins with the current state analysis phase. The operational teams finalize the ABC categorization, run the Pareto analysis, and meticulously map the current physical locations into the software.
Making sure the digital twin is perfect.
Yes, they hunt down any missing ski dimensions because a single incorrect measurement can ruin the volumetric calculations of an entire rack.
Right. And following the data collection, they move into the slotting optimization phase inside the software environment.
This is the computational heavy lifting. The genetic algorithms run their thousands of iterations. The rules regarding crushability and UOMs are validated in workshops with the actual floor managers. The deliverable is a finalized, mathematically verified 3D layout.
But the crucial phase is the third step, the travel plan.
Because knowing where a pallet should go doesn't explain how to move it while the facility is actively processing orders.
Exactly. You cannot move everything simultaneously.
No. The software generates a prioritized chronological relocation strategy. It analyzes the delta between the current state and the optimized state and creates a staggered product travel plan.
So it tells them what to move first.
Right. It dictates exactly which pallets are moved during the night shifts or during off-peak hours, prioritizing the moves that yield the highest immediate reduction in kinetic friction. The change is rolled out sequentially, aisle by aisle, zone by zone.
This level of software-driven orchestration brings up a fascinating structural shift in the logistics industry, which was highlighted by the Prasad Bond piece.
Yeah, this is a huge point.
When we typically discuss revolutionizing industrial supply chains, the conversation is dominated by massive venture capital firms funding hardware fleets of autonomous robots, massive automated storage and retrieval systems.
Heavy metal.
Exactly. But this algorithmic slotting model requires almost zero capital expenditure.
None. Bond points out that spatial heuristics is the ultimate arena for bootstrap software startups. These companies don't require hundreds of millions of dollars to manufacture heavy, expensive physical robotics.
They don't have to manage global hardware supply chains or complex mechanical installations.
Exactly. They are purely selling mathematical logic and software architecture.
The unit economics of that are incredible. But what is truly disruptive is the monetization strategy they employ to sell this to facility managers. It completely alters the dynamic of B2B software sales.
Through what is called a shared savings contract.
Explain how that works, because this is brilliant for bootstrapped companies.
The shared savings model removes the massive upfront friction of enterprise software sales. A bootstrap startup doesn't walk into a facility and demand a $2 million annual licensing fee.
Which a facility manager would just reject.
Exactly. Instead, they offered to ingest the 52 weeks of WMS data, build the digital twin, and run the genetic algorithms with zero upfront cost.
Free of charge to start.
Right. They execute the heat map. Their fee is derived directly and exclusively from the validated reduction in the facility's direct labor costs or the deferred cost of expansion.
So the startup goes to the executive board and proposes, look, we will mathematically reorganize your space. If our algorithms reduce your labor costs by 20% this quarter because your workforce is walking half the distance, we simply take a negotiated percentage of that specific 20% savings.
Yes, or even more powerfully, we will reorganize your cubic volume so you don't have to sign a $5 million commercial lease for a new building. We will take a percentage of that deferred real estate cost.
They perfectly align their profit margin with the operational survival of the client.
Exactly. If the genetic algorithm fails to reduce travel time, the startup makes zero money. It completely de-risks the integration for the facility manager while offering massive upside for the software firm.
It is the ultimate alignment of incentives. But, a facility manager might still view a complex software pitch with deep skepticism. Genetic algorithms and ADICV squared matrices sound great in a boardroom, but how does an operator verify that the math actually translates to the concrete floor before committing to a facility-wide overhaul?
Well, Bond provides a brilliant, frictionless proof of concept for exactly that. It is a 48-hour actionable validation signal.
I love this part.
Any operator can run this test almost immediately without deploying any advanced software to empirically prove the power of volumetric efficiency.
Let's lay out the exact parameters in this validation test for anyone listening who manages a physical space.
Okay. Step 1. You bypass the legacy WMS reporting limitations by simply exporting a raw log of the last 30 days of pick data into a basic spreadsheet.
Just a spreadsheet. And then step 2 involves a manual targeted analysis. You isolate the top 5 highest volume SKUs in the entire facility. Just 5 items out of potentially thousands.
Right. And you calculate the exact physical distance your workforce walks to retrieve those 5 specific items during a standard shift.
Step 3 moves from the spreadsheet to the floor. You physically relocate the inventory of those 5 SKUs so they are positioned directly adjacent to the outbound packing station.
You place them as close to the absolute finish line as physically possible.
Finally, step 4. You measure the immediate localized reduction in the picker cycle time during the very next operational shift.
The results are immediate and undeniable. You don't need a year of data or a predictive machine learning model to run the localized test.
You just move 5 pallets and watch the kinetic friction vanish.
And the margins improve literally overnight. Once the facility manager sees the cycle times drop for just 5 items, the conceptual leap to utilizing an algorithm for the remaining 99,000 items becomes obvious.
And when you scale that validated logic across the entire facility using the full software suite, the final impact metrics recorded by Geodis and Avalon are staggering.
They are. The implementation routinely yields up to a 50% reduction in picking cycle times.
50%.
Yes, it generates a 47% drop in picker travel distance per task. Direct labor costs are reduced by up to 20%. The wear and tear on forklifts and equipment is reduced by 25%.
And ultimately, total order fulfillment capacity improves by up to 25%, all within the exact same physical footprint.
It is the purest execution of restorative engineering. The operation saves millions in deferred real estate and recovered labor costs, while fundamentally saving the workforce from the physical exhaustion of walking unnecessary miles every single week.
The overarching takeaway from this entire analysis is that in industrial engineering, and likely in complex systems management, generally rigorous mathematical logic will consistently outperform brute force capital expenditure.
Absolutely. The geometry problem of a full box is rarely solved by building a bigger box. It is solved by being far more intelligent about how you arrange the contents.
We have mapped out a massive landscape today. We dismantled the illusion of spatial exhaustion and examined how facility managers use commercial expansion to essentially hide operational disorganization.
We analyze the physical toll of inventory digging and kinetic friction.
We walk through the rigorous parameters of Pareto profiling, crushability, and order completion zones.
We establish the absolute necessity of 52 weeks of data and the friction caused by siloed legacy software. We broke down the computational mechanics of the 80ICV squared framework.
We talked about the evolutionary logic of genetic algorithms and the synergistic power of wave picking and S-shaped routing to eliminate human and robotic congestion.
And we also saw how bootstrap startups are leveraging shared savings contracts to monetize spatial heuristics without selling a single piece of hardware. A model proven by that elegantly simple 48-hour validation test.
It represents a profound shift in how operators govern physical space.
It really demands a completely different perspective on the environment around us.
Which leads us to a final thought I want to leave you with. We have spent this entire deep dive dissecting massive industrial operations, robotic supply chains, and complex mathematical matrices. But if you apply this lens to your own immediate environment, your digital desktop, your kitchen, your office architecture, how much of your own daily exhaustion isn't actually a lack of time or a lack of space, but simply a failure of your own spatial logic?
It's a great question.
What are the high-velocity items in your daily routine that you are forcing yourself to walk miles figuratively or literally to retrieve? Look closely at your own spaces, and you might find that you don't need a bigger box. You just need a better algorithm.